So far, we've defined two hyperbolic trig functions. Hyperbolic cosine, or cosh, which is e to the x plus e to the negative x over 2, and looks like a hanging cable. Y equals sinh x, or hyperbolic sine, which is e to the x minus e to the negative x over 2, which looks kind of like the cubing function, but it's curving at a different rate. Next, we're going to define hyperbolic tangent, or hyperbolic tangent, which we pronounce Tange. And as you might guess, Tange is just going to be sinh of x over cosh of x. We're going to take our quotient identity for regular trig and create a definition of hyperbolic tangent using that. Now, any of the hyperbolic trig functions, and in case you haven't guessed, there are 6 of them, can all be expressed in terms of the exponential function. So I can write Tange in terms of sinh and cosh, but I can write sinh and cosh in terms of the exponential function. So sinh was e to the x minus e to the negative x over 2. Cosh is e to the x plus e to the negative x over 2. Now that gives me a complex fraction, but if I were to actually do this division, I would just flip and multiply, and those 2's would cancel. So it ends up being e to the x minus e to the negative x over e to the x plus e to the negative x. Now, we are going to try to get a sense of what the graph of this looks like. What I'm going to do is I'm going to calculate what it is at 0 and the end behavior of this. Okay. So if I look at Tange of 0, okay. Now I could do it this way. I could say, oh, that's sinh of 0 over cosh of 0. That would just be 0 over 1, so that's going to be 0. Okay. So Tange will go through the origin. I could also plug into this version of the formula. I'm going to get 1 minus 1 on top and 1 plus 1 on bottom. 0 over 2 is going to be 0. Okay, now I want to take a look at the end behavior of this. Both cosh and sinh go off to either infinity or negative infinity. So simply knowing where they're going isn't particularly helpful because I'm going to get an indeterminate form of the type either infinity over infinity or infinity over negative infinity. I'm going to work with this. Let's try taking the limit as x goes to infinity of e to the x minus e to the negative x. Now I'm going to just write that as 1 over e to the x, I think. All over e to the x plus e to the negative x, which I'm going to write as 1 over e to the x. Okay. Now I can make an educated guess about this by saying I know that this piece and this piece are just going off to 0. Okay. So if those go off to 0, it looks like we're approaching e to the x over e to the x, which is approaching 1. Now, that's a little bit informal because I'm not really allowed to evaluate just one part of the limit first. If I want to prove that, I can use the technique similar to what we did when we were looking at the end behavior of rational functions. Now, these are not powers of x that we have here, which is what we would have in rational functions, but I've got an e to the x and a 1 over e to the x, an e to the x and a 1 over e to the x. The bigger part is definitely e to the x. So with rational functions, we looked for the biggest part, which in that case was the biggest power of x, and we said let's multiply by 1 in the form of the reciprocal of the biggest part over itself. Now if I do that, we get the limit as x goes to infinity of e to the x over e to the x minus 1 over e to the x squared all over e to the x over e to the x plus 1 over e to the x squared. Now that's the limit as x goes to infinity of, this is just 1 minus 1 over, I'm going to just remind us that we can write that as e to the 2x, because with a power to a power I could multiply the exponents. And on bottom we've got 1 plus 1 over e to the 2x. Now, I can say, oh, that piece goes to 0, that piece goes to 0. This is just 1 minus 0 over 1 plus 0. That's just 1. So very interesting. Tange is going to have a horizontal asymptote at height 1 on the right side of the graph. You'll notice Tange is defined everywhere, so it doesn't have any vertical asymptotes, but it has this horizontal asymptote on the right side. Let's see what happens on the left side. So if I try to take a look at the limit as x goes to negative infinity of e to the x minus e to the negative x, and again, I'm just going to write that as 1 over e to the x. Actually, this time I'm not. I think I'm going to write that still as e to the negative x over e to the x plus e to the negative x. This time, this piece and this piece are what's going to 0. So I can't just look at the formula to know which is going to be bigger. I have to look at the formula together with where x is going. But when x is big and negative, the reciprocal of e to the x is much, much bigger than e to the x, because e to the x is going to be small. So, informally, if these two pieces are going to 0, it looks like we're going to negative 1. To prove that, I'm going to say this is the biggest piece on bottom. Going off to infinity, the positive exponent was the biggest piece. Going off to negative infinity, the negative exponent is the biggest piece. So I'm going to multiply by 1 in the form of 1 over e to the negative x over 1 over e to the negative x. Okay, so this becomes the limit as x goes to negative infinity of e to the x over e to the negative x minus e to the negative x over e to the negative x all over e to the x over e to the negative x plus e to the negative x over e to the negative x. Okay, let's simplify. This is the limit as x goes to negative infinity. That's just going to put another e to the x on top. So this first term becomes e to the 2x minus 1. Same thing here. This just becomes an e to the 2x plus 1. But now, e to the 2x is going to 0 because the exponent is getting big and negative. That's also going to 0. So we get, let's see, I'm going to bump up here. We get 0 minus 1 over 0 plus 1, which simplifies to negative 1. So we're going to have a horizontal asymptote on the left side at a height of negative 1. Now, that just suggests that the graph is going to look something like so. And it does. Okay, I didn't prove that that's exactly what it looks like in between. It looks fairly similar to the graph of arctan, except that the horizontal asymptotes are at different heights. Remember that arctangent would have horizontal asymptotes at heights pi over 2 and negative pi over 2. Tange has horizontal asymptotes at heights negative 1 and 1. Okay, now you are going to be responsible for knowing the definitions. And for Tange, I've got two options. I can think of that as sinh x over cosh x, or I can think of it in terms of e to the x minus e to the negative x over e to the x plus e to the negative x. And depending on the situation, one or the other of those might be more useful. You should know the definitions of these functions, and you should be familiar with their graphs. In the next video, we'll describe the reciprocal functions. I'm not going to hold you responsible for their graphs, although actually they're not too bad, because if you know the graphs of these, you know how to take the reciprocal of things, because you know the reciprocal of something positive is positive, the reciprocal of something negative is negative, reciprocal of something big is small, the reciprocal of something small is big. With that information, you could actually graph the other three. I'm only going to hold you responsible for being familiar with the graphs of these three. You will be responsible for knowing the formulas for and being able to work with all 6 of the hyperbolic trig functions. So we'll get the next 3 in the next video.